Greetings. Here we have one of the interesting questions from continuous time Fourier series. Given the following information about a signal x of t is a continuous time signal. X of t is real and odd. X of t is periodic with period t equal to 2 and has Fourier coefficients a sub k. Now a sub k is 0 for this modulus of k greater than 1. Now half integral 0 to 2 modulus, this absolute x of t squared dt is equal to 1. Now he is asking us specify two different signals that satisfy these conditions. So from this information, from this available information, we must be able to specify two different signals satisfying these four conditions. So we can knuckle down to solve this question like this. Let's make our things simple. See, first of all, you have a continuous time signal. Now x of t is real and odd. Okay. Now anyways, you see, first of all, go to point number 2. This point number 2 is saying that x of t is periodic with period capital T is equal to 2 and has Fourier coefficients ak. So only for periodic functions we can express in terms of Fourier series. So continuous time Fourier series of x of t, let us take Fourier coefficients ak. Okay, so this is what your point number 2. Of course you have period capital T is equal to 2, so we will use it in our later time today. So in this lecture we use this. So you see x of t is real and odd. Now let's go to point number 1. X of t is real and odd. So real and odd. When x of t is real and odd, its Fourier series coefficients, a sub k. Its Fourier series coefficients a sub k are purely imaginary and odd. So this is a well-known fact. So we have to have these concepts always. Okay, see, if x of t is real and even, Fourier series coefficients ak are again purely real and even. But just because of this odd, real and odd, Fourier series coefficients will become purely imaginary and odd. So anyways, we will show this. I'll show this table in our subsequent lectures, like if x of t is real and odd, what must be its coefficients? If x of t is real and even, imaginary. If x of t is imaginary and even, imaginary and odd. Anyway, so we will do those things in our subsequent lectures. For now, just accept this. If x of t is real and odd, Fourier series coefficients must be purely imaginary and odd. Okay, so purely imaginary and odd, so therefore we could write like this. So therefore a sub k is equal to negative a sub minus k. Okay, so this we have. And also as it is odd, a0 equal to 0. Okay, so as it is odd, so definitely we can make a sub 0 equal to 0. So this fact we have from point number 1. And point number 2 is of course this definition, point number 2. Now what is point number 3? Point number 3 is saying that a sub k is equal to 0 for modulus of k greater than 1. So for modulus of k greater than 1 means, now from point number 3 is this. See, he is helping in various ways like this. So ak, let me take it down again. So a sub k is equal to 0 for modulus of k greater than 1. Now what is the meaning of this? That means I can take for k 2, for k equal to 3, for k negative 2, negative 3, for all these things. That means a minus 2 is equal to 0. Yeah, a2 is equal to 0. A minus 3 equal to 0. A3 is equal to 0. So on, right? That's the meaning of this. That means the only unknowns in this problem is a minus 1. A minus 1 is not equal to 0. Yeah? See, for mod k greater than 1, ak 0 means, yeah, for mod k, if I take k is equal to negative 1, it is true, and again I take a1 is again not equal to 0. So 0 is in between minus 1 and positive 1, but a0 is equal to 0. This is evident from point number 1, because x of t is real and odd. If x of t is real and odd, this component must be 0. Okay, so therefore this we can confirm from point number 3. Okay, so this you have to keep it with you. Now what is fourth one? Fourth one, he gave us, what, Parseval's relation. This fourth one is Parseval's relation. So let me take this Parseval's relation. So very important relation we have. So Parseval's relation, what do we have? Average value 1 over t over 1 period, say 0 to t. Now I take x of t, I take its absolute square dt. This is equal to what? Yeah, this is equal to absolute values of square of absoluteness of Fourier series coefficients, provided k is running from negative to positive infinity. So this is what you have. So now what we know is this. Again, from the available data or from the given data, what we have is this. You see, 1 over 2, 0 to 2. And in point number 2, given capital T is equal to 2. So period of this periodic signal is, say, 2 seconds, or capital T is equal to 2 units. Okay, see, 1 by 2. See, here we have 1 by 2, right? 1 by 2 and 1 by t. Okay, so 0 to capital T, where capital T is 2. So 0 to 2, x of t squared dt. So Parseval's relation is this. Okay. As of now, I don't have x of t, but this quantity, this left hand side quantity equal to this right hand side quantity. So this quantity I will take now. I will take this quantity here. So I know only minus 1, k is equal to negative 1, k is equal to positive 1 is valid in the entire range of k. So I will remove remaining k here, and I will just invite k is equal to negative 1 to positive 1. Okay, so we are modifying these limits like this. K is equal to negative 1 to positive 1. Now a sub k magnitude square. Alright, now you know what? This point number 4 is what? So this left hand side quantity is equal to 1. In this case, left hand side quantity equal to this right hand side quantity. So this right hand side quantity must be equal to again 1. Okay, so satisfied. Alright, so now you take it down like this. Okay, so now just expand this. So what you have, a minus 1 magnitude square plus a0 square plus a1, a sub 1 square, this must be equal to 1. Now already we know that as x of t is real and odd, its Fourier series coefficients must be purely imaginary and odd. Odd means this a sub 0 must be equal to 0. So this fellow will become 0. So what do we have now? So we have a minus 1 square plus a1 square is equal to 1. Alright. See here, magnitude wise both are same. Magnitude wise a minus 1 is equal to a1. Yeah, so magnitude wise both are same. So I can take now like this 2 a1 square equal to 1, or I can take 2a minus 1 square equal to 1. So both are same. So from this we can find out a1 is equal to plus or minus 1 over principal square root of 2. Okay, so a1 is equal to plus or minus 1 over principal square root of 2. I'll just get my another page. If a1 is equal to plus or minus 1 by principal square root of 2, then we can make, then a1 could be this. So what do we have? So we obtain like this, a1 equal to plus or minus 1 over principal square root of 2. Okay, so that means if I choose, let me take a1 is equal to 1 by j square root of 2. If I take a1 is equal to 1 by j square root of 2, and if I take its magnitude, definitely we get 1 by root 2, right? Or I can take a1 is equal to, also we can take like this, 1 over, or I can take negative 1 over j root 2, right? So I'll adjust. Okay, fine. a1 is equal to 1 by j root 2 or negative 1 by j root 2. In either case, if I take magnitude for a1, definitely we get 1 by square root of 2. You can leave this negative here. Okay, take this principal quantity positive 1 by square root of 2. So if I take the magnitude of a1, in either case we get positive 1 by square root of 2. Alright. So therefore let me take, this is case 1, this is case 1, and this is case 2. So now with these two cases, with these two forms, we can construct two waveforms or two signals just like that, you see. Now say from 1, if I take this one, okay, now just go for it. Now let me go to this first case. Let me go to this first case. You see this one, ak is equal to minus a minus k. Okay, so what we have is this. Already we have ak equal to minus a. See, these things you have to confirm, then only we can solve these problems. Okay, so but there is no big deal in this. Now I will take k is equal to this one. So a1 is equal to minus a minus 1. Now a1 is equal to minus a minus 1, and I take this one, 1 by j root 2, because a1 is equal to, we have 1 by j root 2. Or I can take like this, or I can choose this one. a1 is equal to, from this definition, left hand side we have this, a1 is minus a minus 1. Now here we will take in the right hand side this form, this case 2, that is minus 1 by j root 2. Are we clear so far? Okay, now from this the possible signals, we have say two possible signals we are going to find out. So the possible signals, let me say, if x of t we have right already, so let me take x1t. So x1t is my signal 1. So you see what is a basic definition. Let me write down the basic definition like this. See, as x of t is my periodic signal with period t, so you can express like this, a sub k e power positive jk omega naught t. Okay, where k is running from negative infinite to positive infinite. So k is running like this. So this is what your basic definition of complex exponential Fourier series. Okay, so now k is equal to your negative 1 to positive 1. So therefore x1t I can put it down like this. So k is equal to negative 1 to negative 1 to positive 1. This becomes ak. Now this is e power positive jk omega naught t. Alright, so therefore let me expand this. Okay, now I'll put like this: a minus 1 e power, this one you see, minus j, k is equal to negative 1, right? So j omega naught t plus a0 equal to, already we have a0 equal to 0, so we can omit a0 here. Now put this k as a1 e power positive j 1, k is equal to 1 omega naught t. All right, now we will choose for now this one. If I choose this one, I'll choose now this case. Let me take my black sketch again. You see, now if I take, see, from this a minus 1 is equal to minus 1 by j root 2, so minus 1 by j root 2 e power minus, what is omega naught? Omega naught is equal to, we have 2 pi over capital T, where t is fundamental period of this signal. So what is t now? T is equal to 2, so therefore we have omega naught is equal to 2 pi, and capital T is given to us what? Capital T equal to 2, so you plug in 2 here. If I plug in this 2, you get pi. So omega naught equal to pi radians per second. Okay, so I'll plug in this pi here. So pi, now this is t. Now yeah, this a1 is equal to, directly we have 1 over j root 2. So 1 over j root 2, again same quality will be applied here. So here we have e power positive j pi t. Okay, so now you can find this. So now what we get, let me take this 1 over root 2 as common. Okay, so what you have, e power j pi t minus e power minus j pi t divided by j, right? So this is what you have. Now you multiply and divide by 2. You multiply and divide by 2, so we get this final answer. Okay, so now because I multiply and divide by 2, and this quantity is what? So this quantity is sine pi t, right? So therefore you have 2 by root 2. You can again multiply and divide by square root of 2. So now what happens? You get square root of 2 sine pi t. So x1 of t, one of the possible signals out of 2, we have like this, square root of 2 sine pi t. Let's investigate finding second signal. Okay, satisfying these conditions. Let's take the second signal like this. Now this is over and out. Now let us go for it. Let us go for this. Okay, now same expansion, use the same definition followed by this expansion. Now we will get like this. Say x2 of t is 1 over j root 2. See, in this case, a1 equal to minus a minus 1 equal to minus 1 by j root 2. So therefore a minus 1 equal to positive 1 by j root 2. This minus will be cancelled out. So we have a minus 1 equal to positive 1 by j root 2. So now you plug in positive 1 by j root 2 here. Okay, so we get like this, and then this will be again as it is. That means we get this one. So 1 by j root 2, and this becomes e power minus j pi t. And now here what do you have? a1. Okay, so what is a1 here? a1 is negative 1 by j root 2. So you plug in negative 1 by j root 2 here. So negative 1 by j root 2 e power positive j pi t. So again you take 1 over square root of 2 here common. So I get, let me take this minus as common there, e power minus j pi t minus e power minus j pi t over j. So again what you do, multiply and divide by 2. So now you get a negative root 2 sine pi t. So therefore the two possible signals are x1t is equal to square root of 2 sine pi t, and x2 of t is equal to negative square root of 2 sine pi t. Okay, now you can take this, this quantity is equal to this, and you can check it out for any other possible signals you have. So for now, based on the given data, following signals, the obtained signals are these two. Yeah, so that's it for today. Okay, so please do watch this lecture series. Okay, please do watch this lecture series until end, and you will learn many concepts in easy language. Okay, thank you, and please subscribe. Please don't forget to subscribe. So please subscribe so that you can have all the updates available. Thank you.